Hey everybody, so this week we are going to be talking about learning and cognition. Let's start out with some basic learning objectives of what we're going to cover in this video. So our objectives for this video are to basically go over localized representations of memory, types of memory, and then we're going to go into memory loss or different things that might contribute to memory loss and what that might look like in people. So let's get into the localized representations of memory. We're going to start by talking about classical conditioning. And a lot of times when people hear that term classical conditioning, they automatically think of Ivan Pavlov or Pavlov's dogs. And that's a Russian physiologist that really kind of pioneered this concept of classical conditioning. In a nutshell, what that means is that somebody is pairing two different types of stimuli, which will ultimately change or shape a response to the stimuli that the person's trying to train. So an experimenter or researcher might start with presenting a conditioned stimulus, which will initially not elicit a response, or we wouldn't expect it to, and then presenting that conditioned stimulus with an unconditioned stimulus, which automatically already has some kind of unconditioned response. So the pairing of that conditioned stimulus and the unconditioned stimulus together, the individual will eventually attribute that conditioned stimulus to the unconditioned response, which then becomes a conditioned response. So that's a lot of kind of psychological jargon, conditioned response, conditioned stimulus, unconditioned response, unconditioned stimulus, or unconditioned response. And we are going to look at specifically the example of Pavlov's dog training to go over that in more depth. But in a nutshell, with classical conditioning, you have something that is already automatically going on. For example, if every time I see a cup of coffee, I have this kind of urge to want that coffee. If someone dings a bell every time I'm going to get a cup of coffee, then eventually over time, if that ding of the bell is associated with me going to get my cup of coffee, I might eventually have that urge to have coffee when I hear that same bell. Hopefully that makes sense. Or if any of you watched the show The Office, there was this episode where Jim was training Dwight to want an Altoid by playing a certain noise every time he gave him an Altoid. And then eventually when he played the noise, Dwight was automatically expecting that Altoid. So that's an example of classical conditioning. And in just a moment, we'll look at Pavlov's study with the dogs in more depth. So let's move on to operant conditioning, which the text also highlights is known as instrumental conditioning. And the main difference between operant and classical conditioning is that with operant, we have this idea of a reinforcer and or a punishment. So a reinforcer is any event that increases the likelihood or probability of a certain response. And a punishment would be an event that suppresses the frequency of the response. So the punishment would make it less likely that that response was going to happen. So that's the main difference, is that with operant or instrumental conditioning, an individual's response will determine the outcome, whether it's a punishment or reinforcer. Whereas with classical, we have that conditioned response and unconditional response that will be paired regardless of the behavior. So let's take a look at this a little more closely. So here's that example of classical conditioning. So think back to Pavlov's dogs. So at first he had this conditioned stimulus, which again, remember, the dog wouldn't have thought to respond to this sound of this bell, or I guess it's a bell here. The dog may not have or would not have necessarily responded to that noise on its own, but he continued to pair that noise with some food, which would increase the dog's salivation, because the dog would smell the food and be hungry and want the food, or have that urge to want food. So this in itself, that the food is the unconditioned stimulus, because a dog's nature is to salivate when it wants that food, right? So that's an unconditioned response at this point. But over time, when he was pairing the sound with this food, however many times it took to pair it where the dog would be trained, that noise itself elicited that increased salivation, because the dog was expecting it to be paired with food, so it had been trained to salivate to this noise. Okay, and so for operant or instrumental conditioning, this is an example of that type of conditioning. So we've got this mouse here, okay, or rat, and so the rat is entering one arm of the maze, and it basically, if it chooses this path, it's going to be led to Fruit Loops, which the rat would like. It's a snack for the rat. But if the rat had chosen this path, it led to a shock, which I don't think any creature would like to be shocked. So basically, over time, the rat learns, oh, if I go this way, I'm not going to like the outcome. But if I go this way, I will like the outcome. So this is an example where the rat would learn that it would like to go this way, and the probability of the rat going this way increases because that reinforcer of the Fruit Loops is there. So it's that increased probability that it's going to continue to choose that way. Whereas it would have an aversive response, which is the shock. So that's the punishment, which would make it less likely to want to go that route again. So there was this researcher, Lashley, who basically wanted to put an engram to this concept of conditioning. But before we go there, let's just kind of highlight that not everything can be labeled as classical or operant conditioning. There's some examples where it's a little more complex, where basically not everything may fall under that specific category. For example, our text gives the example of a songbird that over time is learning its species song, and it eventually learns the song and learns how to call out the song of its species. There's really not necessarily, it's not classical conditioning because it's not paired with anything else. And it's also not exactly operant conditioning because there's not really a punishment or a reward for the song. So our text highlights that sometimes certain examples of conditioning or learning is basically a little more complex than just classical or operant. So coming back to Lashley, considering that the categorization of classical and operant isn't really super clear cut for every example, he set out to find a physical representation of what has been learned. So trying to apply that physically. So one example would be if he had been able to find a connection between two parts of the brain. That would be an example of an engram. So he began this search for an engram, the physical representation of what has been learned. And what he concluded were two different things: equipotentiality, which is that all parts of the cortex contribute equally to complex behaviors such as learning, and that any part of the cortex can substitute one another, and also mass action, which is that the cortex works together as a whole and more cortex is better. So he came to those two conclusions because he was working with rats and teaching them a certain way to go through a maze. He was basically doing some maze learning with these rats. And what he was doing is he started out with cutting parts of the cortex to see if that impacted their learning, which he discovered it really didn't. And then he did more brain damage to the rats, including even full removal of certain parts of the brain. And even then, he found that some rats still maintained their knowledge of the maze, but it definitely was impacted for some of those rats with greater brain damage. And he found that basically it was related to that more brain damage equal less, more impact on the performance of them to continue to go through the maze. So that led him to those two assumptions. But as we're going to go through in the next slide, he actually, researchers actually realized that those were unnecessary assumptions because there's more to it than just the cortex, in short. So let's kind of go on to this next idea. So this is more recent research looking at engram for learning. And Robert Thompson and colleagues basically continued the search, but their thought was, okay, there's probably this more complex process in learning more than just the cortex, you know, and so this little diagram here kind of shows you that they propose that there's kind of like a sequence in the learning path and that there could be different parts of the brain. For example, if somebody's learning something visually, that pathway is most likely going to be different than if they're learning it in an auditory way, or if they're learning it by learning something hands-on. So you can kind of see the sequence here, A, B, C, D, E, F. So they proposed, hey, if the learning for any particular thing is happening at level D, for example, and there's damage done there, then if damage happened at C, will learning have been impacted? They were kind of exploring like where are these points that learning is actually impacted physically. So they did some research with rabbits, and they found, and what they were doing is they were having the rabbits basically trained to respond to a certain tone, and they had paired that stimulus with kind of like a puff, like if you've ever had an optical exam, that little puff in the eye where it kind of forces you to blink. So they had paired that puff into the eye with a certain sound and trained the rabbits to respond to that sound with a blink, basically, even without the puff eventually. So what they found with these rabbits is they interrupted the rabbit's learning of responding to the tone when it had been paired with the puff, and they did it at different levels by inserting drugs or cooling, or basically turning off certain parts of the brain to see what was impacted. And what they found was that the lateral interpositus nucleus seemed to be where the learning that associated that puff with the tone, the eye puff with the tone that was conditioning this blinking, they found that it seemed to be happening at that particular part of the brain in these rabbits. And the reason that they thought that or found that is because when they suppressed that part of the brain by either injecting some drugs or cooling off that section of the brain, the rabbits appeared to not learn or associate that puff with that tone at all. And when they revived that part of the brain, or that part of the brain kind of came back into full functioning, the rabbits were then able to learn. So it basically kind of turned off the learning. And then they also identified with if they did the same thing to a part called the red nucleus, that it basically seemed that the rabbits continued to learn, but they just weren't able to demonstrate their learning. And how they knew that is that the rabbits were showing that they could learn. And then when the red nucleus was suppressed, and then they revived, they basically stopped showing that they had learned it. And then when it was revived, they continued along like other rabbits that had already been trained. Whereas with the lateral interpositus nucleus, they had those rabbits, when they had been revived, basically kind of started back from square one. So let's take a look at this diagram from our textbook. It is a little complex, so let's definitely take a look at it. For me, it's really helpful to look at these graphs here. So we've got these intact rabbits, right? And it's showing that conditioned response is happening, no problem, and then eventually it's conditioned, and then the rabbits blink or respond to that tone, even without having the eye puff. So when that LIP, the lateral interpositus nucleus of the cerebellum, when they basically suppressed it, they found that rabbit did not learn. But then after they revived it, the rabbit was able to learn. And with the red nucleus, they found that the rabbit, when it was suppressed, wasn't demonstrating that it had learned this information, but it showed that it was totally, when it was revived, or when that part of the brain was thawed out, I guess you could say, they found that the rabbits were up to speed with rabbits who had been learning all along. So these rabbits kind of had to learn after this LIP was revived, so to speak, and then so they were kind of starting at square one, whereas these ones, they were learning when the red nucleus was suppressed, but they basically weren't able to demonstrate their learning until it was, recovered after it had been suppressed. So now let's shift over into the types of memory that we have. So we're just going to cover, mainly we're just going to cover what our textbook talks about in regards to these types of memories, the short-term memory and long-term memory. But just know that when we're talking about this, that there is a lot of research on memory, and so there's a lot more information and we could get super detailed on memory stuff because there's just so much out there in regards to working memory, different types of branches of memory and stuff. So just be aware that there's more to it than what we're going to cover in this course. So in brief, we have what we call short-term memory and long-term memory. And really when we talk about consolidation is more so when we're going to talk about this concept of working memory. So short-term memory and long-term memory differ in their capacity. So if you kind of think about memory as this kind of storage unit or filing system, it's got a lot of different, basically there's different capacities for short-term versus long-term. So what I did is create just kind of a brief little table to really go over the differences between short-term and long-term. So with short-term, it requires rehearsal to retain information. If you kind of think about like, if someone, we all have cell phones these days, but let's say you didn't have your cell phone on you and someone said, hey, make a mental note of that, or maybe a better example would be, you don't have anything to write with, you don't have your cell phone, and you see somebody do something illegal and drive off, and you're trying to make note of their license plate number or something. And think about what you might do in that moment. If you're anything like me, you're going to be just trying to remember by kind of like playing it over in your head multiple times what that number was. So it requires rehearsal in order to retain it. And if you get distracted, like let's go back to this example, you're trying to remember this license plate number, or at least the first four characters of the license plate number, if someone starts talking to you or you get distracted, the retention is going to decline. So you may be less likely to remember that information. And the thought here is that once you truly just forget the information from your short-term memory, it's generally lost from that branch of your memory. Whereas long-term, think about one of your earliest memories you can recall. That memory is years old, and definitely when you even have a prompt, or maybe somebody's like, hey, do you remember when we went to Disneyland 10 years ago or something, you know, just kind of somebody's prompting you to kind of help you even remember. It's kind of like you can pull up this memory or this information from even years past, that because it's been stored in your long-term memory. Consolidation. So basically, consolidation is kind of a big word, so let's just kind of go over what it is. What it's talking about here is that it's going to kind of strengthen information into the long-term memory. And we're going to, and basically we're going to talk in depth about this for a moment, okay? So it was initially proposed when memory was first kind of being researched and stuff, that information was in the short-term memory for a certain period until it was consolidated, meaning that it was strengthened or brought into the long-term memory. And so some researchers were like, okay, it's kind of like it just has to keep going around in the short-term memory until it's brought to the long-term memory. But more recent research has shown that it's actually more complex than that, because there's a lot of different types of information, and there's a lot of different components that can basically contribute to how we're processing information. So the first bullet point here is when we think about boring versus emotional information. So there's this concept of arousal, and a lot of times when people hear that word arousal, they think of sexual arousal, but what I'm talking about when I say the term arousal is more of like that activation in your body. So if you think about when you're angry or when you're anxious, your body is aroused, it's activated. Okay, so when you have more arousing or emotional information, it's more likely to get processed into long-term memory quicker. So that's one bullet point of what more recent research tells us. And then our textbook talks about this concept of flashbulb memories. So again, kind of going back to that concept of arousal, what our textbook is telling us is that when something is more arousing physically, it's going to be more likely to be like a flashbulb memory. And I really like that, the way that how they're calling it flashbulb memory and how they explain it as illuminating that memory. Because if you think about some of the milestones in your life, maybe a great achievement that you had, or meeting your best friend, or having your first kiss, you know, all these really exciting moments in your life that were highly activating, highly charged emotionally, highly arousing in the physical sense. It's kind of like a flashlight or spotlight is illuminating that memory, and kind of like the pre and post memories too, like what happened before and what happened after. So the authors of our textbook author of our textbook kind of talks about how it's like a flashlight lit up this memory. So emotional experiences also increase the secretion of epinephrine and cortisol that activate the amygdala and the hippocampus. So the point is that the consolidation of these memories depends on more than the time necessary to synthesize some new proteins. The physiological explanation is that highly emotional experiences arouse the locus coeruleus, which increases norepinephrine and release throughout the cortex, and dopamine release in the hippocampus. So that's a lot of big kind of brain words to basically describe what's going on physiologically in the brain that would make it more likely that a certain memory is going to be captured into that long-term memory quicker and more effectively than perhaps maybe trying to, read two chapters of a textbook that you find boring or something. Another bullet point here is the synaptic tag and capture process. So this is when the brain may tag a memory as like, hey, may be important, but that memory may not be solidified or stabilized into the long-term memory unless like something similar that's significant as well also happens. So our textbook and it's actually kind of relevant to what we just went through recently with the winter storms here in Texas. But think about if you're driving and you go over a patch of ice, or it's a rainy day and you go over some like kind of a scary part of the road, and but you get through it. It might be no big deal, but then when if that happens again, where maybe you slide on some ice, or you kind of slide on some water or something, it's probably going to grab your attention more that, hey, this is happening more than once. This is dangerous conditions. So that's what our author is talking about as a synaptic tag and capture process, where something that's kind of like related happening back to back is more likely to kind of capture that long-term memory. Okay, so working memory. We're talking about working memory in the context of, that basically it's kind of like what we were just talking about as being short-term memory, but some researchers have basically agreed that working memory is a better term for short-term memory because it refers to the way that we store information while we're working with it. So it's not necessarily just this kind of, record player of this information staying in the short-term memory. The working memory is actually referring to how we're working with that information. So researchers and mental health professionals have basically found some different ways to test working memory by doing a delayed response task. And one of the things that pops into my mind when I think about that is the MiniMental status exam, which if you go on to graduate school or you go into any kind of mental health field, it's something you'll be trained on. But I think this is a really great example, a real life example of how we kind of use this information clinically. So when we're working with a patient or client and, let's say you suspect they may have some working memory problems, or even you don't, you're just kind of getting to know this person and assessing them. This is an example of a question that you might ask. You might ask them to name 3 particular objects and repeat that back to you, like apple, table, penny, for example. And in this example, if someone's already having problems, that there's some kind of issue of just being able to capture that information right off the bat. But with the working memory or short-term memory, this particular assessment, after asking a different item, will then ask the person to recall those same 3 words to see if that short-term memory is intact, where they were able to remember 3 words from just one item before. So that's an example of how someone may assess or screen to see if there might be some short-term memory or working memory issues going on. Okay, so to basically wrap up this lecture here, we're going to talk about the different types of memory loss and how those might impact people. So amnesia in general is this concept of memory loss. And an example there would be somebody eating lunch and then thinking they're hungry or needing to eat lunch again 20 minutes later. They may not remember that they ate lunch. Some of y'all may have seen that movie 50 First Dates, where somebody just can't remember who they are the next day. And there's different types of amnesia that we're going to go into. So the textbook doesn't really go through this, but I found it helpful when I was taking a similar course to this to know the different kinds of amnesia. So there's people that have amnesia that is retrograde, meaning that they can't remember things that happened in the past. And then anterograde amnesia is when it's basically when somebody's having trouble remembering future events or things that are more future oriented. And global amnesia is basically having difficulties with all of this. So that kind of gives you a little perspective there. So Corsica Syndrome, and I apologize, there was a typo there, that B shouldn't be there. Corsica Syndrome is, you may remember we talked about it a little bit when we talked about alcoholism. So Korsakoff is also known as Wernicke-Korsakoff syndrome, and it's basically brain damage that is caused by prolonged thiamine deficiency. So the brain needs thiamine, which is that vitamin B1, to metabolize glucose, which is our brain's primary fuel, if you remember. It's kind of like the gasoline for our brain, is that glucose. So severe or chronic thiamine deficiency is common among people with alcoholism. So people with alcoholism may go for weeks at a time with a diet of nothing but alcoholic beverages. And so they're lacking those vitamins and the B1 that they need. And that prolonged deficiency can lead to shrinkage of the neurons throughout the brain and basically cause some serious problems. So people who have some serious Korsakoff symptoms may have problems with confusion, apathy, and of course, memory loss. And one of the unique symptoms of Korsakoff syndrome is that some people will have what they call confabulations, or you may hear the word confabulate, that someone is confabulating that. And so with Korsakoff syndrome, what they are referring to there is that somebody may kind of like make up something about their memory that they don't really know, but they kind of just make it up. And when I say that, they're not really talking about like a fact, like what is the capital of Russia, or what is the capital of the state of Ohio, or something that they may just not know. When they're confabulating, it's normally about something about their life or what they do. So for example, if somebody said, oh, well, did you work last week? And really they don't know if they did or not, they'll be like, oh yeah, I did work, and oh yeah, I need to get to work now. And so they might even act out the confabulation, or kind of really truly believe it themselves, and then even try to act it out. Alzheimer's disease. So most people have heard of Alzheimer's disease. So that is basically something that normally happens later on in life. Early onset Alzheimer's is normally when someone is 60 or younger. And Alzheimer's disease affects 5% of people between the ages of 65 and 74. And then that percentage actually spikes up to half of people, so 50% or more of people who are 85 or older. So it's definitely something that can be an issue the older that people get. So with Alzheimer's disease, procedural skills are usually more intact than basically other types of memory skills. So procedural memory, such as our textbook gave the example of a golf player. Somebody may remember how to actually play golf, but they may have difficulty remembering what was their score or how did they perform this week on these different in these different games. And also, that being said, memory can fluctuate with Alzheimer's. So one day they might remember somebody or some kind of information, and then the next day, or even maybe later that day, they don't remember. And Alzheimer's disease progresses gradually over time. So it may start out as forgetting this information, forgetting that information that doesn't really impact their life seriously, but then it kind of gradually progresses to a more serious memory loss that can include confusion, restlessness, depression, hallucinations, loss of appetite, sleeplessness. So a lot of different symptoms can go along with that. As far as what where did Alzheimer's disease come from, researchers actually were able to use the fact that people with Down syndrome often will get or will have Alzheimer's disease in their middle age. That kind of cued them into that maybe there's a genetic issue going on here. So they began to investigate chromosome 21, which you may already know is highly associated with Down syndrome. So they began looking at this chromosome and found that yes, actually Alzheimer's disease, early onset, particularly Alzheimer's disease, is associated with that same chromosome that Down syndrome is. And there are 2 other genes that are contributed to it, that seem to contribute to it as well. So genes that control that early onset are actually related to a protein called amyloid beta, which accumulates inside and outside neurons and spread from cell to cell. So you may be going, well, what's this amyloid thing that she's talking about? So just a moment, I'm going to pull up some pictures where we can really take a look at what this is visually. So we've got this protein, and I'm just going to call it amyloid, this amyloid protein that's accumulating inside and outside neurons and then spreads. So this protein basically begins to damage axons and dendrites, and it decreases the synaptic input. So it also is decreasing plasticity, and these damaged axons and dendrites sort of begin to kind of clump up together and form what they call a plaque. So it's basically an amyloid plaque, and that will damage the cerebral cortex, the hippocampus, and other areas. So these plaques are kind of, making it difficult for memory to function the way it needs to. And there is an alternative hypothesis, because some researchers have said that, hey, there's some other people have high levels of amyloid, this protein amyloid beta, so why would we just think it's that? So further research has said that there's also another protein called the tau protein in the intercellular support structure of axons, and that the amyloid protein is actually impacting the tau protein. So the amyloid is causing more phosphate groups to attach to tau, and then tau gets altered, and the tau protein cannot bind the way it needs to the axons. So it starts spreading. And so then tau is creating tau tangles. So again, it's kind of like this this waste in the brain that we don't need, these tangles and these plaques, and so it's kind of clogging up the brain and impacting the functioning. So let's take a look at that. So here's an example, just kind of a pictorial example of neuronal degeneration in Alzheimer's disease. So here's, just kind of your healthy neuron, a cell in the prefrontal cortex, just normal neuron. And then you can see here in Alzheimer's, the various stages that a healthy neuron is basically, the dendrites are getting damaged, and then the axons are getting damaged. So you can see the axons just totally severed right there, and the dendrites are like non-existent. So that's just an image of that. And here's an actual slide of someone's brain tissue with Alzheimer's disease. So this is an example of a plaque that we would see if someone passed away from Alzheimer's, and we looked at their brain tissue under a microscope. We would expect to see these plaques and these tangles that are kind of clogging up this brain tissue and also damaging our neurons. So let's come back to this slide just one more time to review infant amnesia. And so that isn't a disorder or anything. It's just something I wanted to be sure that everybody knew. It's a universal experience. Most people don't remember their infancy or even the first couple years of their life. Most people don't even remember hardly anything from their early childhood. Even older children oftentimes don't remember their early childhood. So some researchers have proposed, well, it's because we don't have language development yet, or we don't have, complex processing or reasoning developed fully yet. So that's why. And, but other researchers have said, well, have said that, well, other animals also have this same issue where they don't remember early life or early memory. And so an alternative hypothesis has been that the hippocampus, it has a critical stage of development that animals have to go through before they can really start holding on to memories in the way that we need to, like to remember life milestones and stuff like that. And so some mice studies have suggested that there is a critical developmental stage of the hippocampus where we have a formation of new neurons, of new learning, which will in turn also weaken old memories so that we can kind of make room for that ability. But remember that not all animal research can be translated into human research. So that's just one other thing to think about there. So that concludes our learning and cognition video for this week. Please let me know if you have any questions, and I hope you have a great rest of your week. Thank you.